Hi folks, we'll now take a look at a review of the concept of inverse functions. Okay, so here we've got the notation for an inverse function. It's very important that we realize that when we write f (-1) of x, this is not equal to 1 over f of x. Okay, so the inverse of a function, or the inverse function, is not the reciprocal. Okay. This is a type of inverse. Okay, this is what we call a multiplicative inverse. Okay, and that would be represented by, f at x, and you could put on the outside of all this the (-1). That would represent the reciprocal of f at x. This is how we would denote it. But when we use this particular notation with that, what looks like an exponent but is an exponent, this represents the functional inverse. Okay, and let's review what this functional inverse represents. Now notice here, anytime we're talking about a function, we're always talking about these three representations. Okay, so when we talk about the numerical, we're talking about the individual ordered pairs. So say my function has these three ordered pairs. Okay, if that's what f is equal to, then f inverse is just gotten by reversing the x and y components. So f inverse would be 3, 2, 5, 3, and 1, 5. Okay, so the inverse is just gotten by interchanging the x and y values. Okay, from the graphical perspective, well, here, if you're interchanging the x's and the y's, okay, well, one thing you realize is that anything along the line y equals x will not change. Okay, because here, if the x and y values are the same, well, it won't change by interchanging the x and y components of your points. Okay, but if I have, say, some point xy, okay, and I interchange that to yx, I realize that that x value now becomes my y value, and my y value now becomes my x value, and we see that these 2 points are related in that they're a reflection about this y equals x axis. Okay, so similar to a reflection in the x-axis when we take the negative of a function, or we take a reflection in the y-axis, which is just taking the negative of the input variable, we see that the inverse function can also be seen as a reflection, except about this axis y equals x. Okay. Now the third perspective, the algebraic or analytic perspective, well, again, if I have some function y equals 2x minus 7, well, remember what I'm doing. I'm just interchanging the x and y variables, okay, or the x and y values. So wherever I have a y value, that now becomes my x value, and wherever I had an x value, that now becomes my y value. Okay. Now, of course, we don't normally give functions in terms of x as a function of y. So if I wanted it the other way around, I would just have to solve for the y value. Okay, so here x plus 7 over 2. Okay, so here we have f at x was 2x minus 7. Okay, and f inverse at x is x plus 7 over 2. Okay, and if you were to graph these two lines, you would see that they're just a reflection of each other about the axis y equals x. Okay, so just a quick reminder of the three ways in which we can consider inverse functions. Okay, the last thing I want to talk about, and this concept is going to become important to us in a little bit, is this idea of applying one function after another. Okay, so the idea here is that if this represents my domain of my function f, okay, and let's say I take an input x naught. Okay, what the function f does is it assigns this to y naught. Okay, so that means that the point x naught, y naught, okay, is on f. Okay, sorry, let's show that there. But if x naught y naught is on the function f, that means that y naught x naught is on f inverse. Okay, so here, if I now, immediately after applying the function f, I now apply the function f inverse to the output, well, where is this function going to take me? It's just going to take me back to x naught based on this fact here. Okay, so in other words, here, if I take f and I apply it to x naught, and then to this result I apply the function f inverse, I see that I get right back to my original input. So in other words, if I apply a function followed by its inverse, I get back to my original input, and I can make a similar argument, okay, to justify that if I apply an inverse function to an input, followed immediately by the original function, I again will get to my original input. Okay, and that's what this note is telling us about. Okay, so just a quick recap. Inverse functions are obtained by interchanging the x's and the y's, whether it's the x's and y's in particular coordinates, whether it's the x and the y's on the graph, which represents a reflection about y equals x, or the x and y variables in the equation. Okay. Now, one thing to keep in mind, okay, and I want you to just take a look at this note here, is remember that an inverse is not necessarily a function. Okay, and the way to think about that is if I have y equals x squared and I try to solve for x, okay, I'm going to need to take a square root. So I'm going to have to take a positive and negative version of that answer. Okay, so I end up with something that's not a function. Okay, but what I can do is I can restrict the domain, as you would have done last year, okay, so that the inverse is a function. So in this case here, if I take y equals x squared, but I only take the part where x is greater than or equal to 0, well, then I can reflect this about y equals x and end up with a function, which in this case here would just be the positive square root of x. Okay.